Okay, in today's lesson we'll be looking at part 1.3 of the AQA textbook, which looks at mass number, atomic number and isotopes. If you looked at the AQA specification before at GCSE, this is going to come quite easily to you. You'll probably only be finding a few new things, and it'll be reinforcing what you've already learned. So the learning objectives today define these three key words: mass number, atomic number and isotope, as well as explain the existence of isotopes and why isotopes of the same element have the same properties. Okay, so looking at the atomic number first, the atomic number is the number of protons in a nucleus. Okay, so you're looking here. The atom, it's also referred to as the proton number and has the symbol Z. So sodium has an atomic number of 11, or a Z number of 11. It would be written like this: 11 sodium. And if you look in the center of the atom where the nucleus is, you'll find that there are 11 protons. That's the definition of the atomic number. You can also use the atomic number to find the number of electrons. And in an atom, the number of electrons equals the number of protons. It changes for an ion, because you obviously gain or lose electrons. When we're just talking about an atom, it's equal to the number of protons. We don't include this in the definition because it's only referring to the number of protons. So if you're asked to write the definition, only refer to protons. Now we're going to look at the mass number. There's two definitions of mass number here if you have a look. You've got the mass number and the relative atomic mass number. So if you take the mass number to start with, the mass number is a number that looks at the number of protons added to the number of neutrons within the atom. Because you can't have half of a proton or a neutron, it's always going to be a full number or an integer. And we'll have the symbol A. So the A of sodium is 23. You wouldn't write 0 because you can't have decimals. A is 23. Now the relative atomic mass, these two terms might be used interchangeably in GCSE, but we need to make sure we understand the difference. The relative atomic mass is the mass of an atom relative to 1/12 the mass of one atom of carbon-12. You look at this more in chapter 2, and can be expressed as varying numbers of decimal places. So for example, in the periodic table we actually see that we use the relative atomic mass. The relative atomic mass symbol Fr. The relative atomic mass of sodium will be 23.0. And for a lot of other atoms, you'll see actually you have specific numbers. So you might have 45.2, something like that. And that's referring to relative atomic mass. The key difference is mass number looks at only numbers of protons and neutrons added together, therefore be a whole number. The relative atomic mass of an atom is looking at it in comparison or in relation to carbon-12, so therefore can be a decimal number. The last definition we'll look at today is an isotope. And an isotope of an atom is where the atom has the same number of protons and electrons, but has a different number of neutrons. If an atom has the same number of protons and protons and electrons, then they are the same atom. It doesn't matter how many neutrons they've got. If the proton and the electrons are the same number, then they are the same atom. So we'll look at this example. We've got chlorine 35 on the left here. And chlorine 37 on the right. Now, it's called chlorine 35 because it has 17 protons. It has 18 neutrons. So it has a atomic mass equal to 35. Whereas chlorine 37 still has 17 protons. If it didn't have 17 protons, it wouldn't be chlorine. And it has 20 neutrons, so it has an atomic mass of 37. So as you can see, the electrons and protons are the same. It's the neutrons that differ. And this links into one of our the second part of our second learning objective is looking at how the properties are the same in different isotopes. Okay, these are different atoms. They're the same elements, but different atoms. However, they react the same and have the same properties. The reason for this is all the properties are linked to the number of electrons in the atom, or the number of protons in the atom. As you can see, chlorine 35 and chlorine 37 have exactly the same number of electrons. Therefore, they have the same properties. They're going to react the same way. Again, you look at this a little bit more in the next part. However, just a quick note. It's known as chlorine 30. Chlorine has a relative atomic mass of 35.5. Now, the reason for this is because you look at the contribution from both chlorines. And if you look at the percentage of each chlorine, we'll see why it isn't exactly in the middle. So you would assume if you had two isotopes of chlorine, 35 and 37, then it would be, we would say, an average of 36. However, chlorine 35, in nature, there is 75, if you looked at an example of chlorine, there is 75% of it is chlorine 35, whereas approximately 25% chlorine 37. And we'll look in more detail as we go along this chapter about how we actually work out that relative atomic mass number in a bit more detail later. However, as you can see, it wouldn't be 36, since there's a bigger contribution from chlorine 35 than chlorine 37. It's also worth noting there's actually there could be a lot of different isotopes of chlorine, but these don't contribute towards the relative atomic mass due to the fact some of these isotopes will not be stable, and we only include stable isotopes into the periodic table. So in your booklet you've got this question. Below are two isotopes of carbon that contribute to the atomic mass given to carbon in the periodic table. So now we're looking at carbon. It's a different example. Pause this here, give the example a go and see what you get. Okay, so we're going to look at the answers now. The first one said, name the two isotopes. Okay, so we'll just get rid of this. To name the two isotopes. So the first isotope is carbon 12. Remember, we refer to it as the mass number, and the second one is carbon 13. You might want to write this down here underneath both of the isotopes. The second question says there are actually 15 known isotopes of carbon. Why do these not contribute to the mass number of carbon? The reason is not all these isotopes are stable and therefore do not contribute to the mass number of carbon. Next question is, why is carbon in the periodic table 12 and not halfway between the two isotopes? The relative atomic mass of carbon 12 is based upon the percentage of each isotope. Therefore, there is significantly more carbon 12, so it's a small amount of carbon 13 won't really affect the relative atomic mass. And that's it for that question. Again, this is the isotope of hydrogen. The common name is hydrogen 1 is protenium, deuterium and tritium. The number of protons are 111. Remember, in different isotopes, the protons and electrons are exactly the same. It doesn't matter what isotope you've got, they're going to be the same. If those numbers were different, so if you had more than one proton in any of them, it wouldn't be an isotope of hydrogen. You'd be looking at helium then. The number of neutrons are what changes. So in protenium, you've got 0. In deuterium, you've got 1, and in tritium, you have 2. Then it says, why does deuterium not contribute to the mass number of carbon in the periodic table? It is an unstable isotope. The last thing today, we're just going to look at what AQA actually say you need to know. It says the mass number in isotopes, you need to be able to recall the meaning of mass number, which is referred to as A, and the atomic number, proton number, which is Z. So we know that. I'll be able to explain the existence of isotopes. We've also looked at that. So the actual existence is to do with the fact that different number of neutrons in the same elements, okay, but different atoms. Okay, so that's it for today.